start with this then. So all we're going to do is just simplify expressions. That's it. Okay, but they involve radicals, which makes them a little bit trickier. And because you're in an honors class, we're going to go way beyond square roots. If you were not in an honors math class, you would learn about square roots. That's probably it. You might get to the beginning of cube roots, but it would be just numbers. Like, what's the cube root of 8? 2. That's like an easy problem. We did it yesterday. We're going to get into fifth roots, fourth roots, eighth roots, whatever root, nth roots. It doesn't matter. With whatever variables we have, with crazy exponents. So it's just going to be more complicated than it would be in a non-honors course. You're learning the same material, but we're going to go into a lot more depth, right? Instead of breadth, more depth. So let's take a look at the simple rules. Now, the first question students have asked in the past has been the following. Where do these rules come from? Like, why are you allowed to do it? What mathematically tells you you can do this? And believe it or not, it's your rules of exponents that tell you can do this. Now, it's not obvious because we have not seen a radical as an exponent. But really, if you think back to this rule, take a look. This becomes a to the n, b to the n. Remember that from rules of exponents? When you have a product and you raise that product to a power, that power gets applied to every factor within the product. Now, that rule is what allows us to say, if I have a square root of a product, I can square root each factor of that product. Because the square root we're going to learn in about, I want to say like 2 or 3 lessons, the square root is actually a power. The square root is a power. And that sounds kind of weird, but you're going to see where it comes into play soon. But a square root is actually another type of power. It's a power to a fraction, though. You may have noticed this in your other course at some point, but it's something like x to the 1/3, x to the 1/2. It's a power to a fraction, actually. So the square root function, although it looks different from a power, it applies with the same rules. Bridget.
Yeah, I just noticed that I plugged in values and it satisfied the equation.
And that's the way I would usually prove that this is true, exactly what Bridget just said. Try values. What's the square root of 4? What's the square root of 25? So do 4 times 25, you get 100, right? Square root of 100 is 10. Well, you told me it was 2 and 5. 2 times 5 is 10. So if you just pick a number pick 2 numbers that are perfect squares, choose those as A and B, and you could prove the rule to yourself. Right? So pick A and B as perfect squares and prove the rule is true. And the second rule as well. And the second rule, actually, I think we saw the second rule yesterday, didn't we? Didn't we do an example where there was a fraction involved yesterday at some point?
Yeah.
We may have done something with a fraction, I don't know. I'm trying to think back. Or maybe I was just looking at today's notes and thinking ahead. So anyhow, the rule really is the same for both multiplication and division. Okay, if you have a quotient or if you have a product. So let's jump right into the first one. I see a lot of you already jumping into it. Good. So the square root of 75. Now, here's what I always tell students, and if you follow my guidance here, I promise you you're not going the wrong direction. Break things into perfect squares and not perfect squares. So the rule that we just had said that if we have a number, we can break it into its factors and use the radical for each factor. What can 75 be broken into that has a perfect square? It has a perfect square. 25 and 3. 25 is a perfect square, 3 is not. Take the perfect square and write it first, always. Always write that one first. So we have really root 25 times 3. I'm going to do it one. You would never take all this time. I'm taking way too long to do this, but I'm just showing you. Okay, then I'd break it up like that, and then I would say, well, root 25 is just 5, right? So here's my answer. But that's the process I would undergo for part A. Please don't do this every time like that. Please jump right to the answer. In your mind, you need to be able to see that 75 is 25 by 3, and root 25 is 5. So I recommend that on a test or something, you go right to the answer. If it's really complicated, you got to break up a bunch of stuff, then show your work. But something as simple as root 75, you can take the direct root in your mind, in your head, do all the work, go right to the answer, please. That makes sense what I'm saying? If it's more complex than root 75, then maybe we have to show a little bit of work sometimes. But when they're pretty simple, you can go right to the answer. Good? How about the second one? I can start by breaking up 8 and 6 if I'd like to. Try to break up 8 into a perfect square, break up 6 into a perfect square. It'll be a lengthy process, but it'll work. Or what else could I do if I wanted to? Instead of breaking up 8 and 6 individually, what could I do?
You could put them together and multiply them.
And then?
And then square root that.
Yeah. So when I do 8 times 6, what does that give me?
Negative 48.
Negative, in this case, negative, yes. Negative root 48. The reason this is useful, as Bridge just mentioned, is because 48 contains a perfect square that goes into it very nicely. What perfect square is that? It's not 4.
3, no.
But 3 is not a perfect square. 4, 9, what's after 9?
16.
16. Just try your perfect squares. Does 9 go into 48? No. 4 does, but 4 goes into it twice. I need you to think for a second. Pause, please. If you take 48 and divide it by 4, what do you get?
12.
Isn't 12 also divisible by 4? So 48, if you do the prime factorization, contains 2 4s and a 3. It's 4 times 4 times 3. Remember prime factorization? 4 times 4 times 3 gives you 48. So if you can take something out, it's a perfect square, and then there's another perfect square to be taken out, it means you didn't take out the biggest perfect square. Again, if I were to do this, because it is tempting to do this, I then have to take the 12 and break it up further. And then this becomes... Now, that works, but that is not a direct root. It really isn't. Break this up instead into root 16 by root 3, and there's your answer. That's the direct root. They're both right. They're absolutely both right. And when in doubt, even if you could at least take out a 4 or a 9, take them out. But if you could take out a 16 or a 25 or a 36, take those out because they're bigger and they reduce faster. Next. You got it?
I was thinking
Go for it.
that it would be like plus or minus negative 16.
Remember the whole idea yesterday in the video I was talking to? I might not have gone into a lot of detail if you watched my video about principal square roots. If you take a square root of a number, when it's an expression and you're just evaluating it, it's always the positive root. Now, the only reason this is negative is because it was a negative in the beginning, right? When you solve an equation that says like x squared equals 25 and you root it, it's plus or minus 5 as an answer. So solving an equation, you always use plus or minus, but evaluating an expression or a radical, you use the principal, which is the positive square root. Okay, the negative only comes from the fact that there was a negative in front over here. So what we're going to see here is that there are several roots to take. What else could you have done for this problem? What else could you have done? What was the original? Wasn't it 6 times 8? Or 8 times 6, either way, right?
Yeah.
So I could have actually started there. It's really messy, but take a look. This becomes 4 times 2. And then you say, oh, there's not much more I can do with this, but 6 is actually 3 times 2. Those are not perfect squares, but 2 times 2 gets me back to a perfect square here, which gets me back to, 4 root 3 with a negative. So the weird part about this is you break up 8 into 4 times 2, and you think there's no perfect squares that go into 6, so don't break it up. But if you break it up into 2 times 3, this 2 times 2 gets you back to 4. This becomes a 2. This becomes a 2. 2 times 2 gets you back to 4. So this is a third way to do that same problem by breaking up 8 and 6. It's not very intuitive, though, because you don't want to break up 6 because nothing that's a perfect square goes into 6. So you don't naturally do this. But if you see that there's a 2 left over from the 8, and you can take a 2 out of here, root 2 times root 2 is root 4, which brings you back to 2. And then 2 times 2 brings you back to 4. So 3 different ways to solve the same thing, right? Or to evaluate the same expression. The third one, cube root 25, cube root 10. Suggestions. Suggestions. Tristan, what is your suggestion? Why would you multiply it, Tristan?
Because that's the rule we discussed above, where you can multiply 2.
Yeah, but if you didn't have to, you would do something else, right? Why do you know you got to multiply this one automatically? Because in the previous one, I told you, look, we didn't have to actually multiply it. We could have solved that one with the 8 and 6, right? It turned out. But this one you have to multiply. Why?
Because none of them have cube roots.
Yeah. Nothing that goes into these is a perfect cube. And it'd be messy to break it up. You can break it up into 5s. That would actually work pretty well. You break this into cube root 5, cube root 5, cube root 5, cube root 2. Because we get 3 5s in a row. So that would be useful to do it that way. But when you don't see a perfect cube that goes into them, it doesn't make sense to start by breaking it into anything. So the one way, we'll do it both ways, but the one way to start that is, I think, more direct is what Tristan said by doing this. And then say to yourself, well, what goes into 250 that's a perfect cube? 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64.
5 cubed is 125.
5 cubed is 125. I know. Right? Well, you should know your numbers up to their cubes at least. 6 cubed, maybe not. What's 6 cubed? 6 cubed. I think it's 216, right? Is it 216? Right? Because you're going to get 180, then another 36, right? 216. 7 cubed?
343.
Yeah, did you type it in? Did you get it? I saw you typing away, that's why. 343, yeah. It really doesn't matter at that point, right? You can check them, but you should know that, be familiar with some of your lower cubes at least. And then the cube root of 125 is just 5. We leave this behind as cube root 2. Now, the other way to solve this, let's do this real quick. Ready? We break this into cube root 5, cube root 5. And that comes from the cube root 25 that we're seeing there. And then on the right side, we get cube root 5, cube root 2. That's the other way to solve this problem. But those aren't perfect cubes. The only reason I knew to do that was because 5 repeats itself how many times? How many times? Yeah, and it's a perfect cube then as a result. Cube root 5, cube root 5, cube root 5, that just means 5. And then the cube root 2 carries down. So the second way is actually more direct because it's one less step, but it's not as obvious. Do we all see what I'm saying right now? Root number 1 makes more sense because you see that there's a perfect cube that goes into that. By breaking this up, it doesn't necessarily look like it's going to work, but because you can get a 5, a 5, and a 5, it works that these simplify. If this had been an index of 4 right here, we would have needed a 5, a 5, a 5, and at least another 5, right? We would have needed 4 5s for that to work if it was a 4th root. How about that last one? The last one says root 120 over root 10. Root 120 over root 10. Suggestions. Over root 10. Yeah, you could try to rationalize this and stuff, but it's a little bit messy. I don't know if I would take that route. Yeah?
I would divide 120 into 12 by 10.
Yeah, I mean, you could break this up into root 12 times root 10, and then what happens to the root 10s? So that's the same thing as just dividing 120 by 10, right? And getting 12. So you can just say, what's 120 divided by 10? Anything divided by 10 is one less decimal, right? So it just becomes 12. So this becomes root 12, and then root 12 is really root 4 times root 3. Simply 2 root 3. And that's the way I would break that one up for short. But again, you don't even really, so you don't have to obviously show this work, right? So you could just take the 120 over 10 and write radical 12 as your answer, and then break that up further. So far, okay? It's going to get tougher, that's why I asked. All right, so we did everything with numbers, right? Let's move on to variables now. Now, before I begin something, let me show you a little thing in the corner. And I'm going to show you something that in the past I haven't, but you guys are really good this year, and you guys are doing really well, so I think you can handle this material. I usually kind of just ignore this altogether because it confuses some students. If it does confuse you, it's not the end of the world. You don't really have to memorize this, but it's a little theory. And I was reading about it today, actually, this morning. Anybody know what the answer to that would be? Be careful, because you're going to jump to one answer, and it's probably not right. If you think it's really simple, it's not what it is. What do you think?
X squared.
No?
Or any square root x times square root x.
Okay, but that doesn't help me.
Yeah.
You're right, that it breaks up that way, sure, but that doesn't help me. X? Positive or negative x?
No, wait, don't you have to say that if x is,
Okay, that's good. Actually, make a statement.
like, if x is bigger or equal to 0, x is
That's the problem with this question. That's exactly right. You don't know what x is, okay? So you might want to say, as Yihao mentioned right away, he's jumped to x, which is the common misconception that's what I would put too. Because I would think right away, whatever, square root and x squared, those cancel, don't they? A square root and a square. Imagine x, though, is negative 4 now. Plug in negative 4, square it. What do you get? Take the square root of 16. What do you get? 4. But if we just put x, the answer would be negative 4, because we said x was negative 4, right? So the problem with this is that because of the definition of the square root being the principal root, really, when you're evaluating expressions, your answer is always going to be absolute value of x. Because again, if I plugged in a negative number for x and I do the work, I'm going to get a positive answer out. You follow what I'm saying? So if you think about it in your mind, go ahead and do this. Let x equal negative 2. And then say, okay, I've got this now. That's what I've got. I'm taking the square root of negative 2 squared. But the problem is that when you square negative 2, it becomes positive, and then that answer just becomes 2. So although your starting point was x is negative 2, your answer is simply positive 2. So you pretty much have the absolute value of this number as your answer. That's why that becomes that. Does it make sense, kind of? Okay, and if you're really like, what the hell? Don't even worry, honestly. But when you take a square root of x squared, just remember your answer is absolute value x. I'm not going to take off for it. I'll tell you right now. But you should know that that actually is true. This is true for what kind of roots, do you think? Or what kind of powers?
Perfect squares.
Okay. Even though. Because remember, you have to do it even. Because when you square an even, when you square a negative, what does it become? Positive. When you raise a negative to the 4th, it becomes positive. When you raise a negative to the 6th, it becomes positive. But for the odd powers, you don't have to worry. Because if you had like x cubed, and you do the cube root of that, the answer is just x. Because take negative 2 and cube it. What do you get when you cube negative 2? Negative 8. And then when you take the cube root of negative 8, you get back to negative 2. So you don't have to worry about this problem. There's no discrepancy here with the square root of the x squared. So this is only true, okay, again, only true when this is even and even, when the index and the actual power are even. Anyhow, with that said, let's go into the first one. So, is 3 a perfect square? Is A a perfect square? Be honest, no. Right? I'm not seeing nobody shake their head. How about B squared? Is that a perfect square? Sure. So when I think about this, I break it up that way. And I can do that because of my rules. And because of what we just said, this becomes absolute value B, root 3A. That's a 3. That's an ugly 3. Hold on. Okay? The first one's obviously very easy. How about the second one? Now, before you do the second one, think back to yesterday. Who told us yesterday about what we can do with exponents and indices? What can I do with the exponent and the index if I wanted to? Who came up with that rule? Who was it? Come on. Was it you, George? When it was like x to the 20th, the 4th root of that? We just did, what did we do? When it was 4th root of x to the 20th, what did we do? 20 divided by? Can I do it this time? Can I do 5 divided by 2? I can and I can't. So in a minute, in a lesson or two, we're going to talk about exponents that are fractions. But for now, we're really just focusing on radicals. So the answer would be a decimal, right? It'd be 2.5. So what do? How many of the y's, there's 5 of them, right? Y to the 5th. How many of them can I separate so that it would be divisible by 2? What's a number that I can take away from the 5? How many of them? So what I want to do is this, right? I want to break this into 2 radicals. Some of the y's over here and some over here. What should those powers be so that one of them can simplify? Kate, what do you think? 4. Why 4, Kate? Yeah. So what Kate did was she said, let me figure out what I can break y into so that one of them can be a perfect whatever, so that it's pretty much divisible by the index. The index is what in this problem again? Who remembers this? With a square root, it's not written. What is the index though for a square root? 2. Always 2. We got to remember that here. Okay? When it's a cube root, it's obvious that the index is 3 because it's physically written there.
I put
Oh, okay. And then I see I have a 49. Isn't 49 a perfect square? So let's put that over here with the y to the fourth. Okay, what does this reduce to? This is going to reduce to 7y squared times the square root of y. Well, I don't have to put absolute value here. I didn't take the fourth root of y to the fourth. It only applies this absolute value conundrum when you have the power and the index that are identical and they're even. Is that clear what I'm saying? So I don't have to put the absolute value here because it's y to the fourth power. Again, when these numbers are the same as when you're putting the absolute value there. All right. How about the third one, part C? Suggestions for this, please. Give me some suggestions. Yeah, Max, start us off.
Reduce it to like y to the fourth, the cube root, and y cube root.
Break it into W, you mean?
Like,
Tell me what to break it into, Max.
w to the fourth cube root.
Okay.
Times y cube root.
Divided by.
Yeah.
Okay. I was going to say you can't times it, right? It's divide. All right. Now, what do everybody agree with that first? Makes sense, right? You want to think of them separately? The bottom is easy, right? What's the answer for the bottom? What's the cube root of y cubed? It's just y. Remember, that always cancels. And because they're odd, you don't have to worry about absolute value. So the denominator is very simple. Numerator. What do I want to break up the numerator into? Because clearly I can't do 4 divided by 3, but what can be divided by 3 that's less than 4? 3. So Bridge, what does it break into?
3 divided by 3, just 1, or just W.
Good. So this 3 divided by 3 is going to give me just a W. Very good. And I'm left with the cube root of W over Y. Oops, it's not. Hold on, guys. It's delayed. This happened yesterday for a while. Oh, there we go. Okay. So take a look. This is what I was writing after you saw me. W to the fourth breaks up into W cubed times W. Cube root of W cubed is just W. The cube root of W carries down. So I can think of this as W over Y times the cube root of W. Okay, another way of writing this answer, right? Why am I doing this, by the way? Why do I bug you guys about how to write this differently? I can write it like this also. Take a look. It's just as good of a way to write it. Why am I giving you a hard time, or why am I pointing this out every time? What am I trying to help you with by doing that, honestly? Not just for the fun of it. It's not really fun. Why am I showing you different representations of the same answer?
It's like on the SAT.
Thank you. Standardized testing. Okay? Your answer may not ever appear at all. What do you need to do to your answer? Manipulate, simplify, alter in some way or form. Remember the quiz you guys all just turned in? How many of you multiplied out? How many of you distributed out? How many left in complete factor form? It's like half and half. I was looking at the quizzes. So you remember how you had like a coefficient in your answer in the very front? Some of you distributed it out, and others left it in factor form. It doesn't matter. Either way is right. Traditionally, books leave things in factor form. It doesn't matter. It's the same answer, just like here. Those are the same things. Part D. Part D is a little bit tricky, so try not to fall into the simple mistake here. It's a common mistake I've seen here. 9w squared plus 9u squared. Thoughts? Considerations? George?
You can break it up into 9w squared and 9u squared.
So just do it like this, right? 9w squared and 9u squared. And what symbol am I going to put in between then?
The addition symbol.
So that's a new rule. George just created a new rule for us. Do we have that rule? What's the rule, George? Think back. I didn't mean to call you out, but this is the common mistake. That's why be careful. Oh, it's not even showing up. Let me read.
That
You gotta be kidding me. Of course. What's the rule that we came up with to start today? It's freezing completely, guys. 9w squared plus 9u squared. So you're saying to do it like this right now, but I'm telling you that you can't do this. Why? The rule assumes what do we have on the radical?
You have to multiply.
Yeah, this is addition, isn't it?
Yeah.
So we can't do this, so please be careful, right? That's the common mistake. So I need something that's multiplying. So what should I do? I want to create a factor. Multiplication is a multiplication of factors. So if I need a factor, what should I do to this? Can I write it as? Oh, come on, it's so obvious. It's the easiest factoring technique there is. You always forget the simplest one. Times. Okay, take out the 9. It's just the 9 out front, right? Factor it out, GCF. Now you got factors. 9 is one factor. The quantity w squared plus u squared is the other factor. The 9 becomes a 3. You leave this alone. Please, guys, don't try to square root those. There's a plus sign between them. You can't. Okay, you cannot go any further. No? Okay, airplay is officially out. Part E. Part E, what do we have for part E? Square root of x squared plus 12x plus 36. Clearly, you know not to fall into that case of the last one. You can't break this into radical x squared, radical 12x, radical 36. Please do not distribute the square root to terms. The square root can be distributed to factors only, not to terms. These are all addends or terms. Tristan, what do? Factor it. Whenever you're in doubt here, you need to get factors. What does it factor into nicely?
X plus 6.
Look at that. What a convenience factor. Factor. Okay? Which is really just that. And what's the square root of something squared? Just itself with what sign around it again? Absolute value. So that's what you think of as your answer, right? But don't forget, absolute value. Whenever you take a square root of something squared with a variable in there, it's absolute value. A or B? Examine, right? Examine? Schedule? Nice. I got a couple more minutes this. Hey, can we slide to the next slide? I know you can't see it in front of you. I apologize, but we're going to bear with what we got. So it says, denominator. There we go. It says rationalizing the denominator. The next process, although less important, blah, blah, blah. Let me explain real quick, and because we're running out of time, I don't want to hammer on this. The reason this came about was because calculators weren't around. And when you wanted to do something with square root, you had tables. You had to look at the value, radical 5 in the table, and use an estimation. You didn't have a calculator to do it. So it made life easier to get rid of all the possible square roots, which meant get rid of all the square roots in the denominator. Now, because of calculators, this is unimportant. But it's really important in calculus because it's an algebraic technique to solve equations and simplify expressions. So you will use it in 12th grade. Okay, so we'll talk about this. We'll talk about this to start tomorrow. All right. What you can do tonight is at least do most of the homework. Real quick, that the idea of rationalization was very useful before the invention of a calculator. Before quick, simple calculations could be made. Because if you had something that said, like, I don't know, root 7 over root 2. On your calculator, if you want to find out an approximate value, you can type in root 7 divided by root 2, you get an answer. Pretty simple, right? Now, the problem, though, before calculators were around, you couldn't just say, all right, 7 over 2 is 3.5, so square root of 3.5 is what I have to look up. Square root tables only had square roots of integer values. So you always had to look up a square root value that was an integer. So if you had to look up square root 7, write it, look up square root 2, write it, and then divide 2 decimals, it's really messy to do that. And it becomes a bit clunky or cumbersome. So what people invented was this concept of rationalization. Now, it was around before this, but it was very useful in this technique where you would say, I don't want radical 2 in the bottom. I just don't want to have a radical there. I only want one radical. So let's get rid of the radical 2 in the bottom. Well, ask yourself, if this were not square root 2, another number, for example, what number could this be that it could simplify? What other square roots do we know that are perfect squares that make it easy? Yeah, if this were a root 4, it'd be really nice, wouldn't it? So let's make it root 4. Well, what do I have to multiply this by to make it root 4? What do I have to multiply it by?
2.
Yeah, be careful, specific. Now 2, but
2 squared.
root 2. Root 2. Again, I can't just multiply by 2. I got to multiply by root 2. But if I multiply the bottom by root 2, very good. Because you can never multiply something that's not the value 1, or else you're changing the value. So by multiplying by root 2 over root 2, it's like saying I'm finding a least common denominator. Remember? When you want a least common denominator, you multiply by a fraction, a number over itself. Really, the value is 1. So when you get a result from this, you end up with this. I should put an arrow. It's not equals. Put an arrow. Okay? You end up with a result like this, which is a lot easier to calculate by looking up root 14 and then just dividing that by 2. Okay? Having that decimal. You don't have to worry about this irrational decimal over some other irrational decimal, a value which goes on forever. So you just simply look at one irrational decimal and then cut that in half. Again, not really as important because you have calculators. Now, the concept though, the approach is useful. Because I mentioned yesterday to you guys, in calculus, in your advanced math courses, when you're doing any sort of simplification, you're going to come up with stuff that involve a lot of radicals. Radicals are all over the place. So you need to be able to manipulate them. And one of those techniques is called rationalization. It comes up in a lot in calculus. Some in pre-calculus, you'll see it also. So we're going to go through those stages or those steps. Just there we go. So let's take a look at the first one here. We have root 7 thirds. Root 7 thirds, we've got to think of this as root 7 over root 3. Think of this as root 7 over root 3. How do I make this so that the denominator is now rational? Right now, the denominator is irrational. So we're trying to rationalize the denominator. What do I multiply by to do this? What do I multiply by? Luke, what do you got?
Root 3.
Over.
Root 3.
Thank you. Let's get used to saying that, please. Okay, we got to speak the correct way that we write. So I talk about that a lot, and I do nicely correct you guys, but certain things you need to speak in a certain way, especially when you guys go to college and take your math courses and your professor asks you something. I guarantee you they're going to give you a hard time if you just tell them, I multiply by root 3. It's root 3 over root 3, obviously. Okay, make sure you speak the right way. So we end up with root 21 over root 9, but what's root 9 really? Just 3. And that's always going to happen. It's not a coincidence that the denominator times itself becomes the actual value. All right, that was a 3. It's an ugly 3. How about the second part? Part B. Use part A as a template to help you with part B. Right? Use part A as a template and think about what you would do for part B. What do you got? What do you think?
Root A over root A.
Yeah. Multiply by root A over root A. By root A over root A. What does that make the numerator? Well, root 3 times root A is root 3A. What does that make the denominator? And be careful. Remember what this one was. This is one of those tricky ones. Very good. Not just A, but the absolute value of A. And this is the one that we talked about the other day. I'm not going to go through why that is again. But you need to remember that when you get the square root of a variable squared, the answer is not just the variable, but the absolute value. Okay, if you want to go back to the previous video that's online to look at why that is, if you forgot, go ahead and do that at some point this weekend. But it's always absolute value A there. Good, that's part B. Part C. Instead of being a square root now, you're seeing that we can do this for other types of roots as well. So part C, we've got the fifth root of C over the fifth root of C squared. Now, before I go any further, our rule that we talked about in the last class was take the exponent and try and divide it by the index. Remember that? That's what we kept simplifying. We would look at the exponent and try and divide it by the index if it was possible. Can you do that? Can you take 2 and divide it by 5 and get an integer value? No. I mean, you can do it, obviously, but can you do it evenly? Can you divide evenly 2 divided by 5? No. It's not an integer. So if I want this number right here, this exponent for C squared, if I want that value to be divisible by the index, what must this value be in general? Don't give me a number, give me in general. What must this number be?
A multiple of 5.
A multiple of 5. Very good. If this is a 10, we're good. If this is a 15, we're good. If this is a 20, we're fine. Those all work. Which multiple of 5 will you choose that's easy to get to? That's closest to c squared, or the 2? Yeah. So you want this to be c to the 5th, but it's not. How many c's are missing? If you have c squared, what do you need to multiply by to get it to be a 5th? Max?
C, Q,
Yeah, but I need to multiply by the... Good. The 5th root of c cubed. Okay? Over itself. Why do we do that? We do that so that the denominator can now be simplified into something that is rational. The denominator was irrational to start. Now, what we end up with is the following. The 5th root of c to the 4th over the 5th root of c to the 5th. And the 5th root of c to the 5th is just c. Do we need absolute value this time? Do we need absolute value in the denominator this time? What do you think? George?
No,
How come, George?
because it's not.
Very good, bless you. Very good. Remember the pattern that we picked up on. The absolute value as an answer only occurs when both the index and the power are the same, but when they're even. When they're odd, we didn't have to worry about that. That was part of the proof that we came through to show that. So this is just C. Make sense? Any questions on this so far? So what's your goal? If you were to give me a goal, what's your goal here for this process? To get what? To do what? To change what?
eliminate like a root.
Okay, but be more specific, Max. Where, how,
Eliminate a root in the denominator.
by?
Multiplying by something.
Good. Eliminate some sort of a root that's occurring in the denominator by multiplying by something else with a root to make that root a perfect root. Right? This is a perfect 5th. This was a perfect square. Up there, 3 times 3, 9. Perfect square. Whatever the index is, you have to make it that perfect. You see what I mean by that? So if it's a cube root, you're looking for a perfect cube. If it's a 4th root, a perfect 4th. A square root, a perfect square. In this case, we had a 5th root, so we found a perfect 5th. Okay? Perfect 5ths are like c to the 5th, c to the 10th, c to the 15th. Perfect squares, c squared, c to the 4th, c to the 6th. Perfect cubes, c cubed, c to the 6th, c to the 9th. They're multiples of that value in the exponent. Numerically speaking, though, you need to know your perfect cubes. Right? We talked about 1 is 1, 2 is 8, 3 is 27, 4 is, 5 is, good. And we talked about 6, what was 6 again?
It's like 216.
Yeah, it was 216, but I was like, at that point, you should know at least up to 5. Now, you should know your number 2 to up to like 6 powers, right? 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 is easy. Just keep doubling, right? So know those. Part D, let's put together everything we've done now. Okay, part D is this challenge one. This is what you can expect for a test question, part D, where you've got numerical values, variables, you've got multiple variables, you've got simplification of variables. There's a lot going on here. So if I were smart and I looked at part D, I would say to myself, let me take the shortest route possible when solving this problem, because there are a whole slew of routes you can take. You could start by looking at just the denominator, try to break up 48. You could try to rationalize. You could try to get rid of the x cubed, make it something, or y to the 4th, make it a perfect cube. But you could do all this work, and all that work is in vain because you have a numerator also, right? So start all problems by simplifying wherever possible. So if you didn't think to do that right away, jot that down. Start by simplifying first. Simplify first. So forget rationalization for a moment, please. Only simplify. So I've got 3 over 48. I've got x to the 7th over x to the 3rd. And I've got y squared over y to the 4th. This is how I'm visualizing this. Okay, I'm visualizing this as 3 separate fractions. I'm allowed to do that because why? Why can I do that? Why am I allowed to do this when I was given that up top? Yeah, multiplication signs. It means simply multiply across. So it's the exact same thing I had. I wrote it that way just to visualize that I can now simplify. Simplifying this, what do I get? What do I get? How many x's am I left with?
X to the fourth.
And is that in the numerator or the denominator? Very good. What's left in the denominator? That's all that's left in the numerator, right? Nothing else is left in the numerator for sure. What's left in the denominator? Y squared and 16. Okay? That didn't make sense. Pause and look. 3 over 48 is 1/16. Do I need to put a 1 up here? I sure don't, because I have a variable term. If I didn't have this x to the fourth, though, the 1 becomes my placeholder. It needs to be there. Okay? X7 over x3 is x4. Literally, take 3 of them, cancel them with 3 of these, leaving 4 behind. Take these 2 up top. Remember, I told you guys, please don't subtract exponents. Don't memorize 2 minus 4. Oh, that's -2, which means it's y to the -2, which then has to move down here as y to the +2. Remember that whole thing with the negative exponents? Instead of doing that, just look at it. 4 of them are here, 2 of them are here, these 2 are gone, it gets rid of 2 of these, leaving 2 behind. Okay, literally investigate or simplify by inspection, by literally just looking. Now, at this point in time, we're simplified as far as possible. So then we move on to rationalization. So let's go ahead and rationalize this. Now, I'm going to rewrite it down here so we can do a little work. Before I go any further with this, I want to rationalize my denominator. If I want to rationalize my denominator, I need to have perfect cubes. Why do I need perfect cubes? Why not perfect squares? Why not perfect fourths? Why am I looking for perfect cubes in the denominator? Yeah, look at your index. Whatever your index is means that's what you're looking for. So what's a perfect cube that's close to y squared? What can I make y squared into to make it a perfect cube? Y to the third, or y cubed. So this is currently y squared. I want to make it y to the third. So what do I have to do?
Multiply by y on both the numerator and denominator.
Very good. The cube root of y. Good, Luke. See, and Luke said them. Good, very good. Correct each other. Nice. Multiply by the cube root of y over the cube root of y. That will give me a y cubed in the bottom now. Yeah, it's up in the top also, there's a y, but that's fine. How about the 16? Is 16 a perfect cube? Is it?
No.
What is it a perfect? Perfect square. 16 could be broken into something with a perfect cube because it could be 8 times 2, and 8 is a perfect cube, but you'd still be left with the 2, right? So does that help me much right now? Not as much. Can I make this into an easy perfect cube by multiplying by something? What can I multiply 16 by to get it to be a perfect cube? 4. 16 times 4 is? And 64 is a perfect square and a perfect cube. Ever realize that? It's one of the few numbers. Actually, are there any other numbers? That's a perfect square and a perfect cube?
1.
There are a lot of other numbers. Can you come up? 1 works.
0.
I guess, yeah.
Technically.
0 and 1 work for almost all of them, right? 81 is a perfect fourth and a perfect square. Not a perfect cube and square, though, right? 3 to the fourth.
16 is a perfect square.
Do you figure out what's happening now? Think about something that's a perfect square, like 9 becomes 81, but it could also be square rooted, so it could then become a perfect fourth automatically. So there's literally how many of these that can occur? Thank you. There's an infinite amount of these possibilities because if you have a perfect square of a perfect square, you end up getting a perfect fourth, right? Think about it that way. Anyhow, that's besides the point. What we're getting at, though, is that we need to multiply by 4 over 4 also. Because that makes my denominator now 64 y cubed. It makes my numerator the cube root of 4x to the fourth y. The denominator simplifies nicely. The denominator simplifies very nicely. It becomes simply 4y. The cube root of 64 is 4. The cube root of y cubed is y. How about the numerator? What do I do? Can I leave it like that? Is that allowed? Is it in simplest form? I mean, is it fine? Sure. But if you see this on an SAT or something, when it needs to be simplified, what else can I do? Okay.
You can make the x to the fourth like x to the third and x.
Good. See the x to the fourth? If I thought of x to the fourth as x cubed times x, the x cubed could be reduced because it's cube root. So break up the numerator, like Kate just said. And look at the numerator. Mathematically, that's allowed. Because if I were to go back, x cubed times x is x to the fourth, and then I just have a 4y left over. So I can do that, because now the cube root of x cubed is simply x. Okay? X times the cube root of 4xy, that's left over 4y. Now, again, I mentioned this yesterday, I'll mention it again, and I'm doing this on purpose, not to be annoying, but to emphasize it. This may not be the way you see it. You may see this as a fractional coefficient of x over 4y times the cube root of 4xy. It's the same exact thing, isn't it? Think of x over 4y as a coefficient, as like a fraction, and then since this is in the numerator, you can put it by itself because it's really over 1. So this is really over 1, you get back to the same thing. But you may see it like that with a fractional coefficient in front of the radical or whatever the root is. Okay? It happens a lot with radicals where you don't write it that way. You write the radical on its own. So this would show up as a fractional coefficient. You'll most likely see it like that on an SAT, not the previous line. All right. Does this make sense, the idea of rationalization? So your goal is to get a perfect whatever in the bottom. If it's a cube root, perfect cube. Fourth root, perfect fourth. Fifth root, perfect fifth, etc., etc. Okay? Homework, you guys know. So this is not due until Monday. Do you want to finish, or are you able to finish it without? Okay. Okay, so this will be due on, actually no, Monday's day 6, right? Is Monday day, so
Yeah.
Tuesday. Yeah.
I already did it, but like,
Submit it.
yeah.
Resubmit it if you want to redo it. Yep. Just don't change the file name and it'll automatically overwrite.
Okay.
Okay?